Hi everyone. I'm excited to present our work about C program verification tool QCP. When writing programs, we also want them to be correct, which means they should have memory safety, satisfy certain shape properties, and be functionally correct. Ideally, we want to have a fully automated tool to complete such checks, but this is impossible because this problem is undecidable in general. Complex functional correctness is hard to prove because it requires user-defined predicates and complex mathematical reasoning, which is usually performed in a proof assistant. Existing tools made different trade-offs between automation and expressiveness. However, tools that are capable of proving functional correctness still require a lot of manual effort and is impractical for large-scale programs. To address this, we propose QCP. It achieves high automation, improving simple properties, while significantly reducing the manual effort required for verifying complex properties. For example, this is a C function that reverses a singly linked list. If we only want to check shape properties, we can define a predicate listRep P, which indicates that pointer P points to a valid singly linked list, not mentioning the data stored in the list. Now we put the cursor at the end of the function and click the check button. We can see that the function is highlighted in green, indicating that symbolic execution succeeded and all verification conditions are automatically solved. QCP can automatically prove this simple property without extra manual effort. If we add a bug to the code, such as dereferencing a null pointer at the beginning of the function, and click the check button again, we can see that this line is highlighted in red, indicating that symbolic execution failed. As we mentioned previously, when complex properties are concerned, such fully automatic verification is impossible. In this case, for verification conditions that cannot be automatically solved, QCP will export them to ROC for manual proof construction. Still use the same function, but now we want to prove functional correctness. The SLLPL predicate indicates that pointer P refers to a valid, singly linked list, and the data stored in the list corresponds to the mathematical list L, which has type list of Z in ROC. This time, after clicking the check button, we can see yellow boxes appearing in the code. This indicates that verification conditions that require manual proof are generated on these lines. We can click Calc Proof Gen to generate the calc files. We will obtain 4 files. The Go file contains the statement of all verification conditions. The Auto file includes the verification conditions that were automatically verified. Currently, we have not generated the proof bodies. The manual file contains verification conditions requiring manual verification. Users need to replace the admitted commands with the corresponding proof bodies. We have already completed the proofs. The manual proofs mainly involve deriving mathematical properties, including instantiating existential variables and applying relevant mathematical theorems, such as AP, ASOC, the associativity of list concatenation. Finally, the Go check file is used to verify every Go has a corresponding proof. As you can see, if we delete a proof from the manual file, the Go check make will report an error. Here is the GitHub repo of our tool and the website for the demo. You can find more examples there. Thank you for your attention.